Alright, so we just went over the informal definition, the notion of what it means for a function to be continuous. It involves analyzing the graph of the function. And there are three bad things that can occur: discontinuities, jump, hole. So here we have a hole, or an asymptote, or a jump. Now, sometimes it's good to just be able to do things without having the graph, although the graph is very valuable. And so now let's go over the formal definition of continuity. So this is a formal definition, how we can make it mathematically precise. So a function, say f of x, is continuous at the point x equals a, so here a is some number, a is some number. So this is the expression. We say f of x is continuous at x equals a if, and here's the definition, the limit as x approaches a of f of x is equal to f of a. So this is the definition. I'll put it in a blue box. So here's the condition. This is a very important condition. And so a couple of remarks is that this equality only makes sense if the left side and the right side both make sense. So here's just a comment. A prerequisite for us to even consider this is that we must have that the left side and the right side both exist. So this thing has to be some number, and the right side has to be some number. Okay? So the point is, in order for this to even make sense, the left side and the right side both have to actually equal something, and then they have to be the same thing. And so this definition actually takes care of those three bad situations. So a consequence of this definition is that it allows us to avoid holes. So this definition is a very concise way. This definition, or this condition, let me say condition, so this condition here is satisfied only if there is no hole at x equals a, because if there were a hole, we've already seen a picture. If there is a hole, that means that that either the function just doesn't exist, f of a wouldn't exist, or that the limit and the function aren't equal to each other. So, because a hole, there are two ways you can have a hole. One way would just be you just have this hole here, and so if this is a, so the limit is limiting towards the hole. So that's the limit is taking you to the hole, and then f of a is, but f of a does not exist. Or you could have something either doesn't exist, or maybe you have f of a is like over here. So either it doesn't exist, or f of a is a different point. So you can either have it doesn't exist, but anyways, so either f of a doesn't exist, and then you have this hole, or you have this weird point that's been isolated, and then the two things. So the point is that if the definition is satisfied, then this little picture I just drew is impossible. Okay, so we avoid this picture. So there will be no hole, so that's a good thing. Similarly, there'll be no jump, because if there were a jump, so same idea, if there were a jump, then the limit wouldn't exist. so that I won't draw a picture, but if there is a jump, then the limit itself does not exist. Okay? Because that's just how jumps work, right? So now imagine the graph of the function, there's a jump, so maybe it goes like this, and then goes like that. So you have a jump. So now there's no limit. So jump means no. A jump implies there's no limit. Okay? So this is A. Are you limiting to the lower value or to the upper value? Well, it depends where you come from. There's no well-defined limit. And this definition also guarantees that there's no vertical asymptote. Okay? Because if there were a vertical asymptote, then you can't plug it in. Like, that vertical asymptote means like f of a would be like infinity, which doesn't make any sense. And so then f of a, so I'll put this in quotes, f of a would equal to like plus or minus infinity, which is not a number. Okay? So in order for you to be continuous, you have to compare two numbers, f of a and the limit as x approaches a of the function. And those two numbers have to be equal. And so this is a very powerful condition because it guarantees that we avoid the bad situations. And so this gives us exactly what we want. So this guarantees, so it guarantees that we avoid the bad three situations. Okay, so I just sort of illustrated down here why that's the case. Okay, so you can't have a hole, because the only way you can have a hole, if you have a hole, then either the f of a doesn't exist, and so already the condition is no longer satisfied, or the limit exists, or the function f of a exists, but it's different from the limit. Okay, so the only way that the thing in the blue box can fail to be true is if you have a hole, a jump, or a vertical asymptote. And so if you have the blue box, that means you're avoiding these situations. Okay? So this definition gives us exactly the informal notion. It's a way to realize explicitly the informal notion of what it means to be continuous. Okay? And so we can use this to just verify where things are continuous or not continuous. So let's do some examples of using the definition. So f of x equals 1 over x is continuous for all x except x is equal to 0. Okay? So at x equals 0, we see that f of 0 just does not exist. And of course, we see that the limit as x approaches 0 of f of x also does not exist. But that doesn't mean they're equal. So the point is, neither exists, so they can't be. There's no way they can be equal, because you can only compare things that exist. Okay? So it's not continuous. So what's going on here is that there's actually a vertical spike. So there's actually a vertical asymptote at x equals 0. That's what the graph of this looks like. However, if x is not equal to 0, so for example, at x equals 2, then we see what is f of 2. F of 2 is 1 over 2, and let's do the limit as x approaches 2 of the function. Well, as x approaches 2, so it's not approaching 0, so we can use properties of limits. So that's like the property as x approaches 2 of 1 divided by the limit as x approaches 2 of x. The limit of a constant is itself, as x gets closer and closer to 2, x is getting closer and closer to 2. Okay, so that these two things are, of course, the same. And therefore, so f of 2 is equal to the limit as x approaches 2 of f of x. So by definition, so it's continuous at x equals 2. And you can repeat the same calculation with any other number. So if n is any number that's not equal to 0, if it's not equal to 0, well then what is f of n? It's 1 over n, and n is not 0, so this makes sense. And it's the exact same calculation as before. The limit as x approaches n of 1 over x. Again, since n is not equal to 0, then again it's the exact same calculation as before. It distributes over the division. This is one of our properties. So I'm going to put a little line here so you can see what's going on. And the limit of a constant is just itself, and the limit as x approaches n. As x gets closer and closer to n, x is getting closer and closer to n. So again, the limit is the same as evaluating the function at n. So we see that f of n is equal to the limit as x approaches n of f of x, as long as n is not 0. Okay, so just scrolling back up again, so this function here, 1 over x, it's continuous everywhere except x equals 0. And I'll just give you a quick sketch. You probably recognize this graph. If you were to graph this function, it looks like this. And to the right, it's negative. So there's this vertical asymptote happening as you approach 0. It depends if you're approaching from the left or from the right, but there's a vertical explosion. And you can see the graph is just not connected. You're either on the left side or on the right side, and there's no way to connect the left side from the right side. On the right side, the height is going up to infinity, and on the left side, the height is going down to negative infinity, and it's just not connected. Okay, so, but that's how you use the definition. Let's do another example. What if we have so here are examples. F of x equals cosine of x, or g of x equals sine of x. These are both continuous everywhere. Okay, and we can just look at the graph of these things. So we know what the graphs of these look like. Let's do cosine in blue. The graph of cosine looks like this. It oscillates between 1 and negative 1. It goes on forever in both directions, so it's clearly continuous. And let's look at sine of x. Sine of x looks like this. And I should probably try to get the phase correct. Like that. Anyways, I don't want it to be. I'm now just sort of squiggling, so it's not going to line up perfectly. But the point is, these are both continuous functions, and so every time you have a continuous function, that means that it's easy to calculate the limits. So once you know it's continuous, that means that you can just calculate the limit very easily. Example, polynomials. Polynomials are continuous. Let's just keep going. The exponential function are continuous.